Steel friends, welcome to our next lesson in steel design. Here we're going to take a look at an example to apply some of those yielding and fracture tension limit states that we learned in the last lesson. So here I have a typical splice plate connection. So I have two PL half by 12 inch plates, and they're joined by two splice plates that are sized PL 3/8 by 12. You can see the splice plates overlap the plates in the bottom figure. And I'm just going to color in there's a gap. And so that's really what's meant by a splice plate. We're using those two smaller plates to transfer the force from the plate on the left to the plate on the right. The steel is given to us as A36 steel. We're using 5/8 inch diameter bolts, and the connection geometry is given above. We're asked to calculate the design strength of the tension member based on yielding and fracture. Whenever we do this, we need to consider the tensile strength of both connecting elements. So we need to consider the strength of the PL half by 12 as well as the PL 3/8 by 12 splice plates. So there's not, we can't just check the design of one and assume the other one's okay. However, we do want to be smart about our work, right? And we don't want to do work that's not necessary. So let's just take a look at the areas of these different members. We'll see that by inspection that the design of the PL half by 12 member should control, because if we think about 3/8 by 12, we have two of those splice plates. So we have combined thickness for the splice plates of 3/8 plus 3/8. So that's a total of 3/4 thickness versus the half-inch thickness of the PL half by 12 member. Therefore, we're only going to check the PL half by 12 member for these calculations. Alright, so on to our tension member limit states. So we said our first limit state that we usually check is yielding. And so we're going to check yielding for this PL half by 12 inch member. So our general design equation is that P sub U has to be less than or equal to phi Pn. So P sub U has to be less than, phi is 0.90 for the limit state of yielding, and then Pn is Fy times Ag. Now we're given that this is A36 steel, so Fy should be 36 KSI. And I'll go ahead and jot F sub U down, which is going to be 58 KSI. And again, we can always refer back to AISC table 2-5 for a quick listing of these different material specs for plate elements. We'll head back down to our calculations. Fy is 36 KSI for this particular connection. Ag is going to be, for the half by 12 inch member, half-inch thickness times 12 inches, so a gross cross-sectional area of 6 inches squared. And so now it's just a matter of plugging in the math. P sub U has to be less than or equal to. We plug in the values for Fy and Ag into that equation above, and we can calculate P sub U to be 194 kips. Next, we'll move on to our fracture calculations. So our fracture calculations start in the same manner. We say P sub U has to be less than or equal to phi Pn. So P sub U has to be less than, phi for fracture is 0.75 times nominal strength, which is going to be the ultimate stress F sub u of the steel times the effective area. F sub u is given to us as 58 KSI for an A36 steel. And AE we have from our equations is U, the shear lag factor, times the nominal cross-sectional area at the connection. Now U is going to be 1.0 for this particular connection. So if we refer back to table D 3.1 in AISC, we'll see that this is case 1, where all elements are connected. So all the plate pieces are directly connected in this example problem. So now we just have to calculate the net cross-sectional area. All right, to do this, we have our general formula. Our general formula says that the net cross-sectional area is equal to the gross cross-sectional area minus however many number of bolts we pass through in the transverse direction times the diameter of that bolt plus 1/8 of an inch times the thickness of the plate. And then we said for staggered connections, which is what we have here, staggered bolted connections, we add in a term that is s squared over 4g times the thickness of the plate. And we do this for each diagonal path that we travel. So taking a look at our problem, the diameter of the bolt is given to us as 5/8 inch. The thickness of the plate, we're doing the 1/2 by 12 member, so the thickness is going to be 1/2 inch. S is defined in the previous figure for our connection geometry as the longitudinal spacing, and if we reference back to that, it looks like it's going to be 3 inches, and G, the gauge distance or the transverse spacing, is going to be 2 inches. So showing those terms on a graphic of our connection, S will be the longitudinal spacing between the bolts, in this case 3 inches. And then the gauge spacing or the transverse spacing between the bolts will be 2 inches. All right, we have to determine which fracture path is going to be critical. So I've given some letters here to help us. So we have all those letters. Now the first fracture path you would probably want to check is along the leading edge of the connection. So this is going to assume that the plate is just going to break all the way across this front line of bolts. And again, we're examining the PL 1/2 by 12 member. So the leading edge of the connection is ABCDE. In addition, we're going to consider other paths. So maybe we have something like the one shown here in magenta, where we're constantly zigzagging back and forth across these first 5 bolt holes. So this would be path ABFCGDE. We might also have a case where we travel along the diagonal, but then we split between F and G, and then we come back down to DE. We can keep going with this exercise. We have to keep going until we get all the possible or likely paths that we would expect. So now I'm going to draw one in orange. That's ABFCDE. So instead of traveling back to G down to D and E, it would just split between C and D all the way out. And likewise, we'll do another one that goes down from A to B to C, and then back to G to D and E. Now, I'm not saying that all of these, will control. Only one of them will result in the lowest possible design strength for this tension member. However, it is important that we check all these possibilities because we want to find what yields or what gives us the lowest fracture strength. Alright, the easiest way to kind of assemble your calculations is, I think, to make a table. And so I'm going to go ahead and set up a little table here. In the table, we're going to want to look at those different paths and then do the net section area calculation for each path. We had 5 paths from the previous page, so we'll set up this table so we can look at those different 5 different paths. Just a reminder what our net section area calculation, it's the gross section area minus the number of bolts that fracture path crosses in the transverse direction times the diameter of the bolt plus 1/8 of an inch times the thickness of the plate. And then for each diagonal path, we get an s squared over 4g times t term. So we're going to start with the green path, and that's going to be straight across. So that's A, B, C, D, E. So going across the width, we take the gross section area. Path A, B, C, D, E cuts through 3 bolt holes. The nominal diameter of the bolt holes, the nominal diameter of the bolts were 5/8 inch. So we do 5/8 inch plus 1/8 of an inch times the thickness of the plate, which again, we're only considering the PL half by 12 because that will be more critical. And then we add the diagonal paths. This path did not have any diagonals, so we get 0. And so we get a total net section area of 4.875 inches squared. Next, we want to consider one of the other paths. So I think the next one we drew was the magenta path. So that's going to be ABFCGDE. Alright, so this is the one that kind of zigzagged back and forth. Again, our net section area will be our gross section area, which is 6 inches squared, minus, if you look, the magenta path passes through 5 bolt holes across the width. So we're going to do minus 5 times 5/8 inch plus 1/8 of an inch times the thickness of the plate, 1/2 inch. And now we have to look at the diagonal path. So if you look and follow that magenta path, it follows 4 diagonal paths. So we're going to add to this term 4 times s squared over 4g. If we look at our example, we can figure out that s, the longitudinal spacing between the bolts, is going to be 3 inches, and g, the gauge spacing, is going to be 2 inches. We also multiply this by the 1/2 inch for the plate, thickness of the plate. Alright, and we do some calculations. This will result in a value of 6.375 inches squared. Alright, next path that we considered was the red path, so that is ABFGDE. So ABFGDE cuts through 4 bolts in the transverse direction and has 2 diagonal sloping paths. So we take 6 inches squared, we subtract 4 times 5/8 inch plus 1/8 of an inch times the thickness of the plate, 1/2 inch. And then we're going to add to it the 2 diagonal paths, so that's going to be 2 times s squared over 4g. So 3 inches squared over 4 times 2 times the thickness, 1/2 inch. We do some math here. We could get that this value is 5.625 inches squared. However, we need to take a closer look at ABFGDE when we're kind of looking at, is this anticipated as a failure? So when we're looking at ABFGDE, and you imagine the full separation of the 1/2 inch by 12 member from the connection, right? Remember, fracture is a full separation. Basically, in that full separation, bolt hole C would have to kind of crack and move forward with that connection. So bolt C would have to be still on the member. Well, that means that the red cross-section is subjected to a lower force because that cross-section would only have like 7 of the 8 bolts acting on it. So if we're going to compare path to path to path, we need to kind of increase the area on this path. And we're going to do that by the inverse of how many bolts are on that path. So it's going to be, there's a total of 8 bolts on that path, but only 7 of them are carrying force, causing fracture on ABFGDE. So we multiply this value by 8/7. And so again, this is just a way to kind of scale things up a little bit because we want to be able to compare the likelihood that each of these paths would fail. And because ABFGDE is subjected to a lower load, only 7/8 of the entire load, then we increase its area by 8/7 so that we can sort of compare apples to apples, if you will. I just want to remind you where the 8/7 come from is because when we look at P sub u less than or equal to phi Pn, and I'll kind of draw this out into Pn is the ultimate stress times U times the net section area. If line ABFGDE only has 7/8 of P sub u acting on it, if I wanted to compare P sub u across the board, so I want to compare this value to the other paths, the green path ABCDE and the magenta path ABFCGDE, they all have the full load P sub u. So I'm going to swing this 7/8 to the other side of the equation sign, and then it becomes 8/7. So that's the reasoning for why we use 8/7 times the net section area. It's basically because, as you can see, the red path compared to like the magenta path or the green path, for instance, is not likely to control our design because when we multiply it by that 8/7, it actually results in a higher net section area than both of the previous 2 paths we considered. Alright, and hopefully you are following along with, again, why I said this was only subject to 7/8 a P sub u. But if you don't, I get a lot of questions on this concept, so I just want to kind of point it out one more time. If we look at the red cross-section, and I'm going to circle here in black the bolt holes, if you just go ahead and count those, that's 7 bolt holes, and we're missing that bolt hole at C. So 7 of the 8 bolt holes are effective on ABFGDE, so we therefore multiply by 8/7. Next, we're going to consider the orange path. The orange path goes ABFCDE. So this goes across the, coming across the width of the plate, we pass through 4 bolt holes. So we're going to do 6 inches squared minus 4 times 5/8 inch plus 1/8 of an inch times 1/2 inch. And then we go on two diagonals, so we add 2 times the s squared over 4g times the thickness, 1/2 inch term. And this is subjected to the full load. There's no bolts missing. So this has an area, net section area, 5.625 inches squared. Lastly, we'll look at the cyan. This is going to be ABCGDE. This has the same as the previous, so it goes through 4 bolt holes across the width of the plate, plus it goes through on 2 diagonals, so we're also going to get 5.625 inches squared. So now that we have all the net section areas, we can go ahead and figure out which one's the most controlling. The one that has the lowest net section area will result in the lowest nominal capacity of our section, and so that's going to be the green area, A, B, C, D, E. So we'll continue our calculations on the next page. And as I just stated, path ABCDE controls the design for fracture. With a net section area of 4.875 inches squared. So we'll set up our design equation. P sub u has to be less than or equal to phi Pn. Phi for fracture is 0.75 times the ultimate stress, 58 ksi, times u. U is 1, the shear lag factor, because we have plate connections, so all the plates are connected to each other, so all elements are connected. This was case 1 in chapter D. And then we multiply by our net section area, and we get a total that P sub u has to be less than or equal to 212 kips. We compare that to the yielding capacity. For yielding, we said that P sub u has to be less than or equal to 194 kips. So we're going to be able to draw some final conclusions. I just want to reiterate that on this page. So from yielding limit state, we found P sub u was less than or equal to 194 kips and 212 kips for the fracture strength. So that means that yielding will control, and the all the design strength of our connection in this case for these two limit states is 194 kips. Finally, I want to just mention that so far we've learned just the yielding and fracture limit states. As we continue in the next couple of lessons, we're going to talk about other limit states such as block shear and bolt limit states. So when calculating the full strength of a connection like this, make sure you also will need to consider block shear and all those bolt limit states, and we'll learn about them soon enough.